Okay, let's go ahead and get started. So we're about a third of the way through the semester. We have another couple days to finish up this unit. And that will basically be the end of when we're really focused on R as a language and learning programming specifically in terms of R, but sort of more general concepts as a result of learning R. So next week we'll also talk a little bit about Python. So that'll be the next unit. That'll probably take a day, maybe a day and a half. And then we'll switch gears a bit and start talking about parallel programming, parallel processing, and then dealing with big data and databases and things like that. So that's sort of where we're going over the next 2 or 3 weeks. So we left off talking about memory use and about this idea that R will basically wait to make a copy until it actually needs to. And so we saw this example where we create a function, we create an object y, we pass that object y into the function, and we found that because this function is never really doing anything with the input, the result that we get back, we've got this y, it's got a memory address of this base 16 number. We get out back as from the result of passing y in, and that ends up having the same memory location for out as it did for y. So R was smart enough to realize that there was no need to make an actual explicit copy of this big object, and so it didn't make a copy. So that also happens if you just make a copy just in your regular global workspace. So I think we'll be able to see that here just in RStudio rather than switching over to just command line R. So I'm going to just make this vector y. I think for now we'll just ignore the GC results, although you could look at those to get a similar sort of picture as to what we're going to see with using inspect to look at the memory address. So we see, okay, we've made this vector y. I talked last time a little bit about this idea that internally in C it's represented as a C object, basically so I'm not quite sure whether it's a struct or not in C, but in any event, is this C object that's called the real S expression. Here's the memory address of y at the moment. And now if I, whoops, that was not what I meant to do. I'm not sure what I pasted in, but stop. All right, let's start that over again. All right, I'm going to remake y. I'm now going to inspect x. And we'll see that x also still bears the same memory address as does y. So x and y are basically sort of pointing to the same object, even though R does not explicitly have pointers in the way that a language like C would. But now we're actually going to modify x, and we're going to see what happens in terms of the addresses. So we're going to put a value 5 in for x. We might expect at this point that something has to go on behind the scenes in terms of making a copy, because now x and y are not going to be identical, so they can't just be pointing to the same thing. If we had cleaned everything out and we were doing GC, we should be able to see that there's twice as much memory being used now. And now if we do internal inspect of x, we see that it's got a different memory address than it did a minute ago. So R realized that it needed to make a copy, and it basically took a wholesale copy of where x was, put it somewhere else in memory, made the change to the value 5 that I indicated, and now we've got 2 separate pieces sitting around. Okay, any questions or comments about that? So basically the way this is happening, and we won't go into too much detail here, but I give some details in the notes here, is basically R is maintaining something called a count called named in capital letters that basically is keeping track of how many different names refer to a given object. So when we had y and then we had x gets y, all of a sudden we had there was this named object in R that was related to x and y, said, oh, wait a minute, that object in memory actually has two things referring to it. And so then when I did something like x of 1 gets 5, because named was 2, it realized, oh, I have to make a copy because there's something else referring to this object as well. So I can't just make the I can't just make the change in place and assume everything will be okay, because there are two things pointing into that object. So that's basically the mechanism by which this occurs. It turns out that that this is not handled in as sophisticated a way as you might like, and so you can actually fool it into making sort of unnecessary copies, because the handling of this is not as great as we might like. So one of the things in this pretty quick R that I mentioned back a few sections in the unit ago was that this guy Radford Neal has sort of worked on some aspects of this named functionality to try and improve that. But an example of where this gets fooled, I won't go through all of these examples, but here's an example. If we set A to be some vector and then B to be, then we set B just to be a copy of A. We do internal inspect. Okay, they're both referring to the same memory address. I think this is the named business, and you'll notice there's a 2 next to it. So that's suggesting that internally R has recorded this information that for both the block of memory that A is pointing to and the one that B is pointing to, well, they happen to be the same thing. For both of them, there are 2 names that are relating to that. Well, this is interesting. Now when I change A, I insert a value into A, and I also insert a value into B, how many copies would it fundamentally have to be made if I do this? 1 or 2? Okay, so it seems like we shouldn't need to have 2 totally new objects. We should just be able to modify we should be able to modify one of them in place and have the other one be made as the new copy. So presumably, if we did this, we should be able to make A be a new copy of what A and B had been referring to, change it, and then just change B in place, because B is now the sole thing that's referring to that original block of memory, if it were set up that way. But what we actually see when we do the inspect is we actually see that both A and B have got new addresses. So it must be that it took the original block of memory, made one copy, made another copy, modified both of those. So there's some inefficiency built in here. And it has to do with basically how this named information is set up. That once this is set to be 2, R is not smart enough to realize that in this case it shouldn't have to do the additional copying. So that's sort of getting somewhat into the nitty-gritty of it. In many cases, R will do the right thing. It won't make a copy, and things will be fairly efficient. But it does stumble occasionally. Another thing I'll show you is this tracemem function, which I could probably have replaced a number of these internal inspects with tracemem. I just learned about tracemem in the last year or so after I had developed this material. But if we, where do I have it here? Did I pass it? Thanks. Perfect. Thank you very much. All right. Okay. So here I'm going to insert this tracemem call in A, and now what R will then do is basically alert me whenever it sees that new memory is being used. So here I'm going to make B to be a copy of A. Didn't do anything except for just the usual of what we'd expect. But when I do this, it indicates that there's been some memory, there's been some copying being done. This was the original address of A, and it looks like when I did this, that thing got copied to this address, and somewhat surprisingly, this got copied to this address. So if we look at this, there's no reason there have to be 2 copies made here, so this is actually fairly puzzling. And if I did this, I was puzzled about this, and then this morning I went in and I just did this just in command line R without doing it through RStudio, and when I did it in command line R, there was only this initial line, and there wasn't the second line, which is what I would have expected. So this weird behavior here might have something to do with maybe RStudio is doing something a little bit unusual behind the scenes in terms of doing some extra processing, but I can't can't personally explain what's going on with why there are two copies there. But I think, I'm pretty sure that just in regular R that this would be more, would have more expected behavior.
I just noticed that A and B are different class. One is integer, the other is numeric.
Oh, that's interesting. Yeah, so A, okay, so the colon operator is going to produce a vector of integers. And then, by default, this is just going to be a numeric.
You can try with 1L.
Yeah, okay, that's a nice catch. I bet you're right. So let's go back. Let's make sure to do this as an integer so that A and B have consistent types. Very nice. Extra points to Jan for catching that. So it looks like what was going on was there was not just a copy being made, but it was having to copy from an integer to a numeric as well. And so as a result of that, there were two separate copies being made. So I must have pasted something somewhat different into, when I was trying it this morning, I must have pasted something slightly different than this exact example. Okay, any other questions, comments? One other thing I wanted to show you before, well actually no, I have two more things I wanted to mention. Let's look at this. I just want to look briefly at this example. So if we look at this function here that does a little bit of, at least implicitly in some sense, does a copy here, and then does a calculation with the mean, and returns the result. If you look at this, how much memory do you think would be taken up in running the code in that function, or calling that function or running that function? So when I pass x in, do you think there's going to be a copy made in creating the input variable y? So, is there a specific environment then for it? Well, so there's certainly the frame or the environment of the function. I guess the question is whether we think R is smart enough that it would still be able to just point to the original object, in this case x, that's living in the global environment. So I believe what would happen here is y would for the moment just be basically referring to the same block of memory as x does. And then we do z gets y, so presumably the same thing happens there. There's still no reason that we have to make a copy. We could just have z be pointing to that, and we can now have three things pointing to that same block of memory. What about this? What about if we then pass it along to the mean function? You think we would need to make a copy of the entire object then? So how would we get a better sense for whether or not copies were made in doing that? Well, we could try and sort of reason through it, sort of like string theorists. We could sort of try and reason through it without ever actually inspecting what's going on. I don't actually know anything about string theory, so that might have been an unwarranted crack. But what can we actually do here to try and get a better sense of this? We can look at what's inside the mean function and just see what the operations are. Or we could start doing business with trace mem and that sort of thing. So if we actually look at mean, okay, well that doesn't help us all that much because that says this is one of these S3 methods that we're going to talk about in a few minutes. So it turns out this is probably going to call the default version of the mean function, which is mean.default. So we could look there and see what happens with mean.default. And now we'd have to start doing a lot of logic to see, or we'd have to sort of start looking through each line of code and thinking about what would happen in each of these lines of code and whether or not, depending on what the conditional statements and ifs are, whether or not we get into this block of code, whether a copy would be made at this point, whether we think a copy might be made in doing these various things. And then eventually, looks like potentially there might be a sort that goes on when it does the mean. We'll talk about this issue of why we might need to sort values when we calculate a mean once we were talking about representing numbers in a computer in a few weeks. So depending on whether this block of code got executed, we might need to think about whether the sorting caused there to be new memory to be allocated. And then at this point, R is basically calling into some C code on the some internal C code. And presumably at this point, this is just going to be passed, that whole block of memory is just going to be passed into C. It's now just going to walk through the individual items in the vector, add them, sum them up, and divide by n. And so I wouldn't expect that there would be an additional copy made at this point, but it looks like there might be at the point up there. So any questions about sort of the, obviously we didn't walk through this in detail, but any questions about sort of the logic of how I was thinking through sort of assessing the situation as if I needed to come to some conclusion about that? Comments or questions? Yeah, so we could certainly, that would be, we could sort of take a black box approach with GC, start a new session of R, do GC, or start a new session of R, create X, do GC, run this, do GC again, and then look at that max memory use, and that would tell us. We could also try and, we could, if we wanted to, do debug on this function and step through the function line by line, and then do some internal inspects to see, at each individual position here, whether or not things are getting copied. I haven't, since I just told you guys that traceman was sort of new to me, I don't actually know what would happen if we did traceman with, in some sense, with this. I guess I applied traceman to an object, so I'm not totally sure how I would do it to have traceman be helpful to me here, but maybe if I did traceman on that original value object that I'm going to pass into mean, maybe it would then give me some useful information about copies that were made in mean. I'm not sure if that would be an interesting thing to try. So those would be a number of ways that we could take a look and get a sense for how much memory is being used in some given block of code. And I will probably give you at least one question on the problem set that asks you to sort of walk through this kind of logic to try and think through what's going on. The other thing I just wanted to point out quickly, and this is again sort of at the broad scope of assessing memory use, is we can also, of course, do this from the operating system. And basically, if I can be running R and then have top running in another window, and top should show me how much memory is being used. I'm not quite so used to looking at top on a Mac, so I'm not quite sure where the memory is going to show up. Maybe it's some of these last columns, although they're a bit obscurely named. So yeah, I think it's probably these last columns here. Just finished. Where'd it go? Oh, it just finished. Let me do this in Unix because it's going to be a little bit easier for me to see. So this should use something like 800 megabytes of memory. And if I now look at memory use, it looks like it's not going up that much. It's about using about 1% of machine memory. Oh, here we go. Okay, so now it's showing us that it did use about 800 megabytes of memory in this column here. So we can, it looks like this job by one of the grad students, I think, was using about 4 gigs of memory in this case. So we can monitor this from the level of the operating system as well to get sort of a broad brush perspective on how much memory is being used. Okay, questions or comments? Okay, so let's move on and talk some about object-oriented programming. So this is section 4 of the unit. So it turns out that R actually has 3 different ways of doing object-oriented programming, and I was just preparing some of the material in Python the last couple days, and Python has a really nice kind of clean, elegant approach to doing object-oriented programming. And so then as I'm coming back to look at this, look at R, the fact that R has these 3 different systems for doing object-oriented programming, it's a little bit frustrating. So there are lots of things I like about R, but the object-oriented side of it is a bit confusing because there's so many different ways to do things. That being said, we're focusing on R, so we're gonna talk about object-oriented programming from the perspective of R. So how many of you have done some programming with some object-oriented programming language? Okay, so a reasonable number of you. So this is going to be kind of old hat to you guys. Hopefully you won't get too bored. But the basic idea of object-oriented programming is that all of the operations that you're doing in your processing are built around these things called objects. And objects have a class, and basically the idea of a class is it's sort of like a template for an object. So objects are going to have various member components and that contain data of some sort. And then there are going to be methods that operate on the objects in that class. And those methods basically do things with the member data, and everything is sort of bundled together in a nice coherent package. So that's the basic idea of doing object-oriented programming. One example of it that we see, sort of a canonical example in R, is if we look at the lm function. If you run the lm function, it's going to give you back an lm object. So it's going to give you back an instantiation or a realization or an instance. Those are all terms that get thrown around. An instance of the lm class. It's going to give you back an object in that class. And then there are lots of methods that are associated with that class that will then carry out various operations on lm objects. So they'll do things with the residuals, or they'll provide a summary of the results. So you can run some plotting, or you can do some you can calculate some information criteria on the model, or things like that. So the idea is that that's a nice way to go, because there are all these different sort of functionality. There's all this different functionality that's associated with using linear models. We might as well bring that together with the actual information that's stored about the linear model, or the results of fitting the linear model. Okay, so the first approach to object-oriented programming that was developed in R is something called S3. This, I don't know where the 3 comes from. The S presumably comes from the fact that R is a language developed out of another language called S that was developed at AT&T back in the mid-'80s. So the idea is that S3 classes are, they're really common. Lots of different packages use them. They're used a lot in the base stats package. They're very informal in the sense that what they are is they're basically a list, and then you can create methods associated with objects in this class, but there's no actual real formal definition of what are the components of an S3 object. So I could get back an LM object and then tack on a new component to it just as a user, and R will not complain and say, oh, your new component is not something that's part of my definition of my class. So it's not a very strictly defined class system. Okay, so another idea with object-oriented programming is this idea of inheritance, that you can have a class and then have another class that inherits from that original class, and then the idea is the new class that inherits from the old class. It inherits the properties of the old class, but then you can also have additional new properties that are associated with the class that's doing the inheriting. So an example in R, oftentimes if we're working with the object-oriented stuff, we'll need the methods package. So I'm going to load the methods package in here. So what I'm doing here is I'm just fitting a linear model, and then I'm fitting a generalized linear model where YB is just a vector of binary variables. And so if I look at the class of mod 1, it says, oh, it indeed is an LM. That was from fitting my linear model. But if I look at the class of mod 2, which actually shows me 2 classes. And what this means is that the GLM class is a class that inherits from the LM class, which makes sense because a GLM is sort of a specialized version of an LM where there's sort of more stuff going on. So the idea was that when people were writing the GLM class, they said, you know what? It's going to have a lot of the same functionality and stuff that's in the LM class, so let's not rewrite all of that. Let's inherit that from the LM class. And then on top of that let's add on the new stuff that we need for doing GLMs. So that's the idea. That's the idea of how inheritance is used in this particular situation.
If we ask whether mod1 is a list, it'll also say it's true, and that's because all of these S3 objects are built upon lists, and so they're inheriting from the properties of being lists. And so we can do things like ask what are the names of the things in mod1. So this is going to give us the member components or the member data that are part of the object, sort of things that like we would expect. We can ask whether mod2, which was that GLM object, is an LM. It says, yeah, it is. And then we can ask what are the various methods that are associated with a given S3 class. So I'm going to use this methods function that I believe is in the methods package, and it'll tell us that the methods associated with the LM object are the sorts of things we might expect. Things like a formula and a log likelihood and regression diagnostics like DF betas and things that you may have heard of, the hat values, things having to do with AIC, all the sorts of things that you might expect.
What does the star mean in the output here?
Yeah, so that gives us this little message down here saying non-visible functions are asterisk. I think that probably means these are functions that are not really meant to be used by the casual user, but I'm not totally sure of what. Yeah, in terms of non-visible, I mean, if we wonder if we try this, whether we'll be able to see the function if we just print out its name. So okay, so like vcove is, that's in there. What was one of the visible ones? All right, so the generic vcove function, which we'll talk about what a generic function means in a minute. That one we can see that, but I don't see vcove.lm. Whereas if I do print.lm, I do see print.lm. So I think it's that this v. Let's see if I can get it by using this scoping operator. Oh, it's not an export object. Okay. I wonder if that means it's actually in there. So this has to do something with how packages are. I think it has to do something with how packages are set up and which functions are both visible to the user and available to the user to be run. So there are some functions in packages where the person who's developing the package only intended it to be run by another function within the package. And so those things will not be what's called exported and made available or visible to the user. And then I'm not sort of remembering all the details. There are probably some distinctions between what's visible to the user and what's actually usable by the user. So I think all of this has to do with sort of those nitty-gritty details of that sort of thing. So that's basically what's going on here. Other questions? So the other thing we can do, I was going to say something else, but I sort of lost track of where I was. We can also create our own. We can create our own S3 class. So let's see an example of doing that. So I'm just going to create this object that has some information about me, and all I need to do to create this object and give it, tell it to, and then tell R that it has the class indiv, is I just need to create a list with the pieces in it. And then I just need to sort of brute force tell it that the class is whatever character string I give it. So this is in part the sense in which I meant that these S3 classes are not very formal. I can just sort of create one on the fly. I could create another object that has different pieces in it and say that's also of class indiv, and R will not complain, even though it's crazy to define two different instances of the same class that have totally different things in them. So R does not do a lot of careful checking of things. One of the things that comes up when we talk about object-oriented programming in general is this idea of constructors, which are basically functions or methods associated with the class that are designed to create a new instance of the class, a new object in the class. So here I'm just going to create in the S3 approach a constructor function that will create new indiv objects in the indiv class. And all I'm doing to do that is, again, it's very informal. I just make my list. I say that that's the name of the class, and then I return the object. And so I've just sort of created a constructor on the fly.
I just chose to name it this, but I didn't have to choose to name it that, but it's a common thing. It sort of makes sense to name the constructor with the same name as the class, and then it's sort of all sort of clear what class is being referred to, and that's just sort of a convention there. So if I do that, that will indeed allow me to, you know, and then I could make another one that. And then I could look at me, I could look at Sam, et cetera, et cetera. I can also sort of do anything I want. I can say that change the class of me to some other class just by changing the name of this class attribute. So there's lots of stuff you can do that wouldn't make a lot of sense. Okay, so we've talked a little bit about methods associated with classes. So let's talk about a little more in detail about that. So the basic idea is that we're going to have these things that are called generic methods, and then we're going to have class-specific methods. So for an example of that is, remember I have my, I guess I'm sort of redefined, I guess I called them mod 1 and mod 2 up there, and for some reason I decided to make them mod and gmod here, but I'm running an LM and I'm running a GLM here, so just to create the objects. And then you'll see that I'm using the same name of function summary on both of those objects. But those are two rather different objects. One of them is an LM, one of them is a GLM. It means different things to summarize those. You have to do different, you know, there might be different test statistics, different ways of computing confidence intervals, things like that associated with LMs and GLMs. So part of the power of doing object-oriented programming is that you can define a generic function like summary and then define the correct behavior associated with using that function on objects of different kinds, of different classes. So if we do this, we'll see that here's the result of summary on an LM object. And here's the result of summary on a GLM object. And you can see you get somewhat different stuff back. If you do the LM object, you see it gives you back residual standard error, R squared, F statistics. If you do it on the GLM, you see it gives you back AIC, deviance, number of scoring iterations for having done the optimization to fit the GLM. So that's this specific behavior that's specific to the different kinds of objects. And what's going on here is basically that, I'll illustrate this with the mean function rather than the summary function for no particularly good reason. So maybe I'll actually do it with the summary function. So if we look at summary, what's actually going on behind the scenes is, first what happens is summary gets called. And summary is this thing called the standard generic. And when we see a line that looks like this, basically what's happening is R gets to this line and says, wait a minute, this is a generic function. I need to go figure out what's the class-specific function or method that I need to go use, that I need to dispatch in the language of object-oriented programming. So it basically, this standard generic is basically going to inspect the class of the object that's coming in, determine what kind of object it is, and then dispatch the correct class-specific method that's appropriate for that object. So if it sees that an LM object is going to come in, it'll dispatch and call summary.lm, and there's code for, here's the code that is run when you call summary.lm. Looks like it's fairly long, but it takes the object in and then does all sorts of stuff to it. And summary.glm is a totally different function that does the summary stuff needed for a GLM. So it also operates on an object, the input object, but it does different stuff. So that's the basic idea of generic and class-specific methods. Comments at this point? Okay, so we can also define our own method. So if the generic method's already defined, then we don't need to redefine it. We could just define a print function that's relevant, say, for our indiv class, and we wouldn't need to define the generic. But if the generic hasn't been defined, then we need to actually write the generic function. So it's pretty simple. If I want to create a generic function called summarize, this is basically all I need to do, and that's the sort of form it needs to take with the ellipsis, and needs to take object as the first argument. And then in the S3 style, it's pretty easy to there's not really much to do in terms of creating the class-specific method. I just name it as the name of the generic dot and then the name of the class that I'm defining it for. So this sort of goes back to what we were talking about on Monday in section, this idea that the period means something specific here in terms of object-oriented programming in R, but we also can just name things willy-nilly with dots in them, so it gets to be a little bit confusing potentially. But here the dot is very important. So if I do this, and I now call summarize on that me object, which was of the indiv class, it tells me the generic hasn't been found, so I need to run the generic, or I need to create the generic. And now what this summarize function does is it operates on the me object, and it does what I asked it to do, which is it just does a cat and then prints out some summarization information. So obviously a silly example, but that illustrates the syntax of how you would do this. So there's another sort of detail here that's actually quite useful to know because it sort of explains some mysteries that have come up so far in class and some things that seem like they're mysteries when we're using R, which is that when we actually do summary on an LM object, its summary itself is not actually doing any of the printing out of the information. So what summary is doing is it's creating a new object, which is a summary.lm object. So if we do this, and then this, I can ask what's the class of out? And it says it's a summary.lm object. So the magic here is that whenever you just type the name of an object at the prompt, what's actually going on behind the scenes is R is calling a print method that's specific to whatever the class is of that object. If that object doesn't have any particular special class, or there's not a print method defined for that class, it's just going to call print.default. But if there is a specific method defined for that class, it's going to call print dot whatever that class name is. So if we just pass an LM object, if we just type the name of an LM object at the console, it's going to go call print.lm on that object. And if we type out, or if indeed if we had just entered summary of mod, what it's actually going to do is it's going to call print.summary.lm, because summary.lm is the class of the object. So when you do summary of mod, summary itself is not actually doing the printing out. This is creating an object, and then print.summary.lm is doing the printing out. So here, and if we wanted to see that, we could actually see what that, so that's why I guess I had this in here. Turns out that's sort of hidden from us, and I need to do a little bit more machination to look at that function. But this is actually the print method for the summary.lm class. So things get a little bit involved there. But basically, the thing to realize is that whenever you just type the name of an object, then what you're really doing is calling a print method, and those print methods can be modified and specialized to particular kinds of objects. We could also, for example, look at print.defaults and see what that looks like. We can look at print.lm, see what that looks like, so we can get a sense of what's the underlying code that's being run. And if we create our own class, we can also create our own print dot and then the name of that class, and we can then tailor whatever printing out we want to do to show that. And so remember I had the mod object that was just the result of fitting a linear model. So this doesn't tell us very much, but it does sort of print this out in sort of a clean format. The thing to remember is this in its underlying state is just a list. And when I print out a list, you guys know what printing out a list looks like. It has the square brackets, and maybe it has the names with dollar signs and all that in there. Well, you'll notice this looks very different than printing out a list, and the reason is because it's not just calling the default printing method for a list, it's calling the specific print method for an LM object.
Okay, so we can also define class-specific operators, just like we can class-specific sort of standard functions. So this is the way that you would do it. We could, for example, see if there are any other plus methods defined for various classes. It looks like there's one defined for the date class and one for something called the POSIX class, which I think also has to do with dates and times. But if I want to define my own plus function, I can do that in backticks as we sort of expect as we've been working with operators. I can have it do whatever it needs to, and so then, if I define it this way, then I can take my me object, I can add 15 years of age to it, and then I can create some new object that's called the older version of me. And we can also make class-specific replacement functions. So just like we've seen replacement functions, I can make functionality that will allow this kind of code to operate where I've got this replacement method age, and the way I do that is by saying age and then the assignment operator in backticks, and that's the way that I define these new operators. You'll notice I had to define the generic in this line here, and the standard thing that you need to do when you do this is you need to follow a sort of standardized format for what the arguments are. So that these give you just some examples of what these things look like. Okay, questions about that? Okay, so I have on the in the notes, and I'll ask you to think about this for class on Monday. Here's the challenge, and if you're able to figure this out, then it says that you understand sort of what's going on with these classes and methods. So what I want you to do is I want you to figure out how to, if you simply type Q at the command line in R, have it quit from R and return you back to either back to Windows or back to the command line in Unix without asking you any questions. So you should be able to type Q and R will just exit cleanly without doing anything else. So that's the challenge, is to figure out what machinery you need to set up behind the scenes to get that to happen. Okay, so that was S3. That was the S3 approach. S4, as you might expect, came after S3, and it was essentially an effort by some of the R developers to formalize the class definitions and make an object-oriented approach that was more formal than the S3 approach that we've just been talking about. So S4 is used in certain places in sort of the R ecosystem. It's used a lot for bioinformatics stuff, which are in the bioconductor project. It's also used in LME4, which fits linear mixed effects models. And there are some differences from S3. One of just the syntax differences is if you want to retrieve a member component or within an S4 object, you need to use @ instead of the $. So you need to do the name of the object and then @ and then the name of the component. The components in S4 programming tend to be called slots. So that just means the slots where the data are held. And one of the ways that S4 is different than S3 is that S4 sort of carefully checks to make sure that if you have an object in a particular class, that it has the slots that are expected of that class, and only those slots. That you can't have extra stuff in there. So basically, when we create a new, and we have to sort of formally create a new S4 class in a way that we didn't have to do for S3. So basically, we're going to use the methods package, and to create a new class, I'm going to have to use the set class function. I have to give it the name of the function, the class, and then this representation is basically saying what the slots are. And sort of interestingly here, we're actually telling R what the types of the, or essentially really what the classes of the slots are. So we're defining in advance what are going to be the pieces of this class, the pieces of the objects of this class, and what kinds of objects they're going to be. So let's actually switch over to R and just try this out here. Okay, so I've made an indiv class. Now this is an S4 class. I guess that's not true. Okay, so it looks like there's still my old indiv object, but presumably this class does exist and I can use it, even though it doesn't seem to be printed out when I just type in div. So the way we create a new object from an S4 class is we call the new function, and that basically behind the scenes calls a constructor function that constructs the object. I think the method that's getting called behind the scenes is a method that is a method actually called initialize. So if we do this, and now we type me, we'll see that it prints out the information in a somewhat different form that sort of indicates to us that it's one of these S4 objects. Because it says, oh, these are slots, gives me the name of the slot, or no, it gives me the name of the slot, and then it gives me the value that's inserted in that slot. So I didn't particularly like the date that I gave it. I must have given the date in the wrong format. If we do something like this, you'll notice that it just filled in a missing value for age because I didn't pass in an age when I instantiated the object. I just gave it the name and the birthday as the initial values. But interestingly, if we do this, and instead I give it the name and the age, but not the birthday, it says, oh, it doesn't seem to like that. So it says, invalid object for slot birthday in this class. Something about should be or extend the class date. So I believe what's happening here is it's trying to fill in a default value. So it knows that there are these three slots, name, age, and birthday. And if I don't give it an input for one of them, it's trying to fill in some default value so that it makes sure to fill in values for each of those three. But apparently, what seems to be going on here is there's no default value for the date class, which was the third of that was the class of the third of the slots. So it complained because it didn't know what to stick in there for this slot, and so it balked and it gave me an error message. So that's in part what I mean by this idea that with these S4 methods, they're more formal, and R does some checking to make sure that everything sort of hangs together. So I'm going to do that again. I can go in and change a value in a slot using the @ syntax, so that should work. Oops. So now I have name, age, birthday. I've sort of messed things up here because I've changed the age without changing the birthday. So if you were really programming in a more formal way, you would want these two things to be connected such that you couldn't willy-nilly go and change one and have it be inconsistent with the other slot. So there are ways to set things up within R so that those sorts of checks would be put in place. So I think, why don't we stop there and we can pick up there on Monday. Yeah.
So can a member of the S4 class be a member be a S3 class?